Hello everyone, and thank you for your time today. I'm one of the co-founders of VisualLogic. What I want to share with you today is not just another AI IDE, not another coding assistant, and not another low-code platform. I want to talk about why we believe the AI era demands an entirely new programming foundation. Right now, most products in this space follow the same playbook, take existing programming languages, and add AI on top. We took a completely different path. And I believe by the end of this presentation, you'll understand why that difference matters and why it creates a fundamental competitive advantage. Let me start with a core observation that most people in this industry are overlooking. For the past several decades, every mainstream programming language, whether it's JavaScript, Python, Java, or C++, was designed with one assumption in mind. Humans write code, and compilers execute it. The entire paradigm assumes that humans are responsible for understanding structure, while compilers are responsible for execution. Now, we're forcing AI into this system. We're asking AI to generate and understand millions of lines of linear, implicitly structured text. Look at what happens: context overflow, hallucinations, unstable code generation. And here's the critical insight: this is not a model intelligence problem. It is a representation problem. The languages themselves were never designed for AI to work with. This is a fundamental misalignment. So there are essentially two paths the industry can take. Path 1 is what everyone else is doing, the industry standard approach. You start with legacy languages like JavaScript or Python, you use standard IDEs, and then you add an AI patch on top. The bottleneck here is clear: AI is forced to parse millions of lines of text that were designed for humans. The outcome is line-by-line generation with fragile context. Path 2 is what we're building, the AI-native path. We start with a new language designed for both humans and AI from day one. Then we build a projectional IDE specifically for that language. And only then do we add AI as a first-class citizen. The outcome is explicit, component-based structure that enables parallel generation. Our core belief is simple: if AI is a first-class citizen in the programming process, then the programming language itself must be designed for AI. Based on this belief, we made 3 strategic decisions, and the order is extremely important. First, we designed a new programming language. We call it VL. It's AI optimized in its structure and syntax from day one. Second, we built a visual IDE specifically for VL. This is not versus code with plugins, it's built from the ground up for this language. Third, and only after the first two were in place, we added AI generation capabilities. AI generates VL structure, not patches on legacy code. This is the exact opposite of what the industry standard does. They start with existing languages, use existing IDEs, and then try to add AI on top. We believe this order is not just a preference, it's a strategic necessity. Now let me explain what makes VL fundamentally different as a language. VL's entire syntax is defined in a single document, about 100 kilobytes. We internally call it the Bible. This single document covers UI, logic, backend, database, and deployment, all in one unified syntax. Compare this to the traditional full-stack knowledge base. If you want to build a modern web application, AI needs to understand React documentation, Node.js APIs, database query languages, deployment configurations, and dozens of constantly changing frameworks. That knowledge is scattered across hundreds of documents, APIs, and frameworks that are always evolving. With VL, AI only needs to learn one document to master the entire stack. There is only one source of truth. This is not a minor convenience, this is a structural advantage for AI comprehension and generation. VL is not code-centric. It is component-oriented programming. In VL, everything is a component. And every component naturally contains 3 things, what we call the Trinity. First, properties. This is data, configuration, and state. Second, methods. This is logic, actions, and business logic. Third, events. These are triggers, interactions, and event handling. This is the atomic unit of VL. There's no syntax boilerplate. We follow composition over inheritance. It's pure logic. When AI generates a VL program, it's not generating thousands of lines of text. It's generating components with explicit properties, methods, and events. This structure is what makes AI generation stable and predictable. Now I need to address the 2 most common misconceptions about VisualLogic. The first question I always get is this a low-code platform? The second is VL just a domain-specific language? Both are reasonable questions, and both answers are no. Let me explain the differences. Low-code platforms hide complexity. They use templates and workflows to trade expressiveness for ease of use. And when you need complex logic, you have to escape to code. DSLs, domain-specific languages like Skull or Terraform, solve one specific domain. They're not general purpose. VisualLogic is fundamentally different. VL does not hide complexity, it structures complexity. VL is a general-purpose programming language with full expressiveness. You can build any application structure. There are no fixed templates, no preset workflows, no capability ceiling. The essential difference is this: low-code hides complexity, VisualLogic structures complexity. This is not a semantic distinction, it's the core of what we do. Now I want to share what I consider the most important technical insight behind VisualLogic. Most AI programming tools today do one thing: natural language to code. It looks magical, but it's fundamentally unstable. Why? Because natural language is ambiguous, and code is precise. Without a stable structure in between, problems are inevitable. In compiler design, we almost never go directly from source to machine code. We always have an intermediate representation, an IR, which provides stability, analyzability, and transformability. In VisualLogic, VL is that intermediate representation. Human intent, whether expressed in natural language or direct manipulation, converges to VL. VL then expands to executable code, visual IDE representation, and runtime. This is the aha moment. VL acts as the stable layer between ambiguous human intent and precise executable code. This architecture makes AI generation verifiable, rewritable, and highly compressible. We're used to thinking of IDEs as code editors with extra features. But this is a historical artifact. Traditional IDEs are always centered around text, even when they have visualization features. Text is primary, structure is implicit. VisualLogic takes a completely different approach. Our IDE is not a tool built around the language, it is a projection of the language itself. Code view and graphical view are two projections of the same underlying structure. You can switch between them freely. Edit the graph and you edit the code. Edit the code and you edit the graph. There is zero information loss. This is bidirectional, lossless projection. Why does this matter for AI? AI is not good at understanding implicit structure hidden in linear text, but AI is very good at operating on explicit structure. A projectional IDE puts AI and humans on the same level. Debug in the graph, fine-tune in the code, same structure, different projections. Now let me talk about why this architecture creates real competitive moats. The first moat is token efficiency. In our system, one line of VL can expand to 200 to 400 lines of traditional code. Traditional AI code generation consumes roughly 10,000 tokens per feature because it generates verbose syntax, boilerplate, imports, and framework patterns. VisualLogic generation consumes roughly 1,000 tokens per feature because VL is pre-abstracted components and pure logic. This is a 10x difference. And here's the key insight: as AI-generated software scales, token cost becomes real economic cost. Representation efficiency becomes the bottleneck, not model intelligence. Whoever has the most efficient representation scales the furthest. This is a long-term structural moat. The second moat is generation speed. Traditional AI generates code sequentially, line by line, file by file. Total time equals the sum of all files. VisualLogic AI generates in parallel. UI structure, logic, and database can all be generated simultaneously. Total time equals the longest single file, not the sum. This is possible because VL's component architecture naturally supports parallel generation. Each component is independent. There are no implicit dependencies that force sequential generation. Parallelism breaks the linear constraint of ELMs. This means 10x faster generation for complex applications. The third moat is scale. Traditional AI code generation is limited by the context window. With a 128,000 context window, you can handle maybe 50 files, small to medium applications. After that, token overflow kills the project. VisualLogic breaks this limit. Because of component isolation and compressed representation, we can handle 500 plus components. Enterprise-scale applications become possible. This is not incremental improvement, this is a category change. Traditional tools hit a ceiling, VisualLogic scales beyond it. The fourth advantage is collaboration. If you've used AI programming tools, you've experienced this. AI changes code you didn't want changed, AI breaks structure, human and AI conflict on the same files. This is what we call text layer conflict hell. When multiple agents, whether human or AI, edit the same text, conflicts are inevitable. VisualLogic solves this with the component layer. Humans focus on architecture and verification, AI focuses on generating component logic and properties. Collaboration happens at the structure level, not the text level. Components are independent units, they can be developed in parallel without overriding each other. This is surgical precision, no more merge conflicts. AI should not compete with humans for code, it should collaborate on structure. Let me conclude with our fundamental thesis. As software scale increases and AI participation deepens, whoever controls the representation layer controls the system's ceiling. We are building three things: a new language with minimal syntax and pure logic, a new IDE with 2D projection, a new AI layer with parallel agents. These three layers together form the VisualLogic stack. We are not building a tool, we are defining the paradigm for the next era of software creation. VisualLogic is not AI-assisted programming, it is AI-native programming. A new language, a new IDE, a new way for humans and AI to collaborate. If you're interested in the future of programming, I invite you to follow our journey. This is just the beginning. Thank you.